Problem 6. A circle, gamma, has radius 1. A line L is such that the perpendicular distance from L to the centre of gamma is strictly between 0 and 2. A frog chooses a point on gamma whose perpendicular distance from L is less than 1 and sits on that point. It then performs a sequence of jumps. Each jump has length 1, and if a jump starts on gamma, it must end on L, and vice versa. Prove that after some finite number of jumps, the frog returns to a point it has been on before.
So, this is a problem about a jumping frog. The frog is initially resident on a circle at a point of its choosing, distance less than 1 from this vertical line, and the radius of the circle is also 1. And the frog is going to jump from between the circle and the line alternately, always jumping a distance of exactly 1, and where it can, not returning back home. And you're supposed to show, well, the point of the problem is to show that eventually the frog is forced to return to a point which it has previously visited. And in fact, what's going to happen is it's going to go back to its original launch point. The secret of getting this problem correct is to draw a very accurate diagram using compasses and rulers and all that stuff. If you draw it freehand, it's a lot harder to work out what's going on. Anyway, let's do it. Here's the frog. The frog jumps to the line and then jumps back. So we've got an isosceles triangle here because those both have distance 1, and these distances are also both 1. So you may know that a quadrilateral where the sides all have equal length must be it's called a rhombus, and it's a parallelogram with all its sides being equal. If you don't know that, then you have to prove it and convince yourself that it's true. But it is true. Anyway, so we've got a rhombus here. Now the frog has not revisited its original launch point, so off it goes again. It jumps a distance 1. There are 2 possibilities, but it came from here, so it goes there. It goes down here, and another distance 1 here. And for exactly the same reasons as before, you get another rhombus here. Now, this line is parallel to this line, because they're opposite sides of a parallelogram, and this side is parallel to this side because they're opposite sides of a parallelogram. Therefore, if you just look at the top side and the bottom side, they are parallel line segments, and of course, we know they both have distance 1. We could consider the figure formed by those 4 points. Well, one of the ways of characterizing a parallelogram is that it is a figure with a pair of opposite sides which are parallel and of equal length, just like this. So this figure here is a parallelogram. The new fact we learned is that this line is parallel to this line. This new magenta line is very interesting because what it would enable the frog to do is to look into the future. If the frog were at its launch point and it was wondering to itself, I wonder where I will be after 4 jumps, it doesn't have to look on any electronic map. What it can do is just draw or imagine a line down here, parallel to the line over here, and see where it meets the circle. And it turns out that that's where it's going to land after 4 jumps. Now, in a sense, we probably finished now, because if the frog now launches from here and does another 4 jumps, it's going to end up, well, on the same magenta line meeting the circle. It's going to end up back home. So after 8 jumps, it's going to be back home. But you know, let's push it through and look at the details. So doing this carefully and slowly, the frog is now sitting here. It jumps 1, it jumps 1, and you've got your parallelogram down here, a new one, a rhombus, and then it jumps again, and we've got a new parallelogram rhombus there as well. And for exactly the same reasons as before, the vertical line here is parallel to the vertical line on the right. It means we're dealing with the same vertical line. So indeed, when you launch from this point, you end up there after 4 jumps at where you did start. So viewing the situation from when you actually started, that's 8 jumps, and you are forced to come back home, and the problem is done. There are other ways of doing this. We've done it using geometrical diagrams. You could do it if you know about vectors, you could do it purely symbolically using vectors. Or if you know about complex numbers, you could use them instead. This is the beginning of a wider story, and let me see if I can give you some things to think about. So here's the assembled diagram of all 8 points. There's a little bit more that's true that isn't in the question. You see there's these points here, the intermediate bouncing points. What happens when the frog starts from one of those? Well, it bounces around the same path of length 8, coming back after 8 steps to where it was at the beginning. And the argument for the existence of a vertical line repeats for them. So they are on a vertical line as well. But there are other things you could do. You could, instead of having a circle and a line as your launch and landing points, you could have 2 circles. Or you could have 2 lines which are skew, or 2 lines which are parallel, 2 lines which are mutually perpendicular. There's lots of stuff to investigate and work out what happens in those circumstances. Enjoy.